In this lecture, we are going to talk a little bit about modulation techniques. In other words, we're going to move away from talking about the physics and the theory of how the physical environment operates in molecular communication. We're going to take our first steps towards talking about molecular communication as a communication system. So it's reasonable to remind ourselves of the block diagram model of communication, which we've talked about many times. So we have a transmitter. We have some message that comes into the transmitter. Transmitter. We have a channel. We have a receiver. And at the output of the receiver, whatever we detect goes into a message sink. Okay, sometimes people add encoders and decoders on either side of the transmitter and receiver, but this version of the diagram is sufficient for our purposes right now. So, up till now, we've talked about how the channel works. So we've talked a lot about in the channel how the physics of the channel operates. We talked a lot about diffusion, chemical reactions. All these are mechanisms that occur in the channel, and they're potentially mechanisms that could occur at the interface of the channel, at the transmitter and the receiver. So right now, what we've previously talked about, so here, from there to there, basically at the interface of the channel to the transmitter, the interface of the channel to the receiver, and everything in between, that's what we've talked about so far. So that's the physics of the channel. Or the physics of molecular communication. We're going to talk about now, we're going to expand that. So we're going to start here. We're going to talk about from end to end, the transmitter to the receiver, and that is actually the communication theory. Of molecular communication. And what better way to start that discussion than by talking about modulation. So you should be very familiar with this, but modulation is the means by which the message is represented on the channel. In conventional communication systems, we're very familiar with how this works. If we have a message, let's suppose it consists of one bit, 0 or 1, we pass that to the transmitter. The transmitter encodes it by, for example, on-off keying, which we'll actually see a little more about in this lecture. In on-off keying, we send for example, a 1 volt signal down a wire for a 1, and for a 0, we send 0 volts. That is sent along the channel, and then the receiver's job is to figure out, was the original signal after the attenuation of the noise through the channel, was the original signal 1 volt or 0 volts? So that's an example of how to represent a digital message in a way that can be transmitted across an electrical medium, in particular a wire. So now what we have to do is figure out how can information be represented chemically. So there is one way that you're probably thinking of already, and we actually talked about it in an earlier lecture on the biophysics of molecular communication, and that's DNA. So in DNA, a molecule is used to actually literally encode digital information. So we saw how this worked. At each position, you could choose one of 4 nucleobases. So basically you have a 4-area encoding scheme. So you can imagine what you could do in that case is you could create a custom DNA of arbitrary length, encode your message into it, release it into the channel, it diffuses along, and then at the receiver, what you would do is you would pick up that DNA and read it, and there's your message. That is actually a serious proposal for molecular communication, but we're actually not going to be focusing on that too much. We might talk about it in a later lecture, depending on how much time we have, but we are not going to focus too much on that way of communication. What we're instead going to think about is, so in molecular communication, we normally consider either indistinct molecules or a small number of distinguishable molecules. That is your reservoir. So we talked about reservoirs. Your reservoir will contain either maybe one or maybe a small number of possible distinguishable sets of molecules. So what you're going to do is you're basically going to reach in here, pick one, and send it into the channel. The identity of the molecule you pick is not very important. So one way to think about it would be you have a big bag of indistinct balls. So they're all balls with the same color, same size. You reach in there and you pick one, and you're going to use that ball to send your message, and you dump that into the channel. This is distinct from the DNA example. So an alternative would be to have a huge number of distinct molecules so that you could basically write your message on the molecule. That's like the DNA example. In that example, basically you would have molecules in here for each possible message you want to send. You'd pick the specific one representing the message you want to send. You would dump that one in the channel. So this is not what we're going to super talk about in this course. We, like I said, we might talk about it briefly later, but we're not going to be talking about it very much because it's actually not a very common assumption in molecular communication. This I'm going to call inscribed matter. And I'm just going to write down here, not really in the scope of this course. So like I said, we're gonna be thinking about how to design our modulation schemes with this basically this bag of balls that we can't really tell apart too well, and it really doesn't matter which one we pick in order to send it through the channel. To design modulation schemes of that kind, you can think about the kinds of dimensions that you can use when all you have available are indistinct balls. So what are some things that you could change if you have a bag of indistinct balls, or maybe 2 or 3 bags of balls of different color, but like I said, just a small number of choices. So this is the kind of question that molecular communication designers grapple with when they're thinking about modulation. So when balls are indistinct, or when molecules are mostly indistinct, you can use the following properties. To transmit information. By the way, there is an excellent survey paper that came out on molecular communication modulation. I'm going to be using some concepts from that one. It's actually not my paper. It was published by another group, but it's quite good. I'm going to put a link when I upload this lecture. I'm going to put a link in here. And so just look for it on this page. Actually, I'm not going to upload it. I'm not going to put it in the video lecture. When I upload these notes, I'm going to put it in these notes. So look for it on the uploaded version of these notes. Okay, so what dimensions? Basically, what we're looking for is what degrees of freedom we use when we have either one or a small number of groups of indistinct molecules. So we can do things like timing. We actually gave some examples in the first lecture, but we're going to deal with these in more detail now. So we can change the timing. In other words, information. So let me back up. Let T I be the time of release of the ith molecule. Then the vector T1, T2, and so on, up to Tn, can be used to express information. Using n molecules. So a simple way to think about this would be if you want to send a binary signal. So if you want to send a 0, maybe you send molecules at time 0 and 1. And if you want to send a 1, then you send molecules at time 2 and time 3. So this would be, this is in the form of T1, T2. So we're sending 2 molecules. To send a 0, we send them at 0 and 1. To send a 1, we send them at 2 and 3. We're always sending 2 molecules. It's just that the times at which we send them are varying. You can see just a couple of features about this. We'll actually talk a lot more about timing, but you can see, for one thing, you can separate these arbitrarily far. So you could have 0, 1, and like 1 million and 2 million. Depending on how your diffusion works, it's you can separate these by so far that it becomes extremely unlikely that an error will be made. However, the cost for that is that you have to wait arbitrarily long for your message to arrive. We're going to see, in fact, that in this case, noise is additive timing noise given by the first arrival time. So that's, again, that's for absorbing receivers. First arrival time is relevant for absorbing receivers, but if your receiver is absorbing, then what you'll see is that you transmit at this time. The first arrival time is whatever time you released your molecule plus the first arrival time, giving you basically additive noise. So that's nice because it recovers a lot of what we like to think about in normal communication, which is how to deal with additive noise channels. Another common one, quantity. So notice in the timing example, the number of molecules was always the same. In other words, n. We can also vary n to send messages. So we're going to, just for the sake of discussion here, we're going to separate timing and quantity arguments or types of modulation, and we're just going to talk about one at a time. There's no, in a minute, we're going to talk about hybrid modulation schemes where you can do both at the same time, and that's fine. But just for the sake of our discussion and for simplicity, we're just going to separate them. So we'll see you can either do quantity or time. This is sometimes called concentration shift keying. Or CSK. Because the changing number, i.e., or actually the changing value of n, let me be more precise. Changing value of n leads to, or allows you to, send information, but n changes the concentration. So as an example, the simplest example is on-off keying. So what you can do is if you want to send a 0, you send 0 molecules. So n equals 0. And that's off. If you want to send a 1, you could send some other number of molecules. In fact, let's be a little more precise about that. Let's define a number, capital N, as the number of molecules we send for a 1. That's on. So here, this is where we use counting noise. So for a non-absorbing receiver, the number of molecules in the receiver is the noise. So we talked about that a little bit in a previous lecture. For a non-absorbing receiver, the number of molecules in the receiver is random. So you can imagine that if there are no signaling molecules whatsoever in the environment, you release none will get to the receiver. But if you release n, then at least some will hopefully get to the receiver. So you'll be able to count some. So you can imagine the random number of molecules that end up in the receiver will end up being your received signal. And the fact that that's random suggests how the noise can be modeled. Another way in which modulation can work is by type. So in other words, if you have, now remember I said the molecules can be indistinguishable or there can be a small number of distinct types. So if you have, let's say, M distinct types of molecules, you can use them to send information. By varying the identity of which molecule is used. Sometimes this is called molecule shift keying. Or MOSK. So as an example, as a binary example, let's say you have, if you want to send a 0, you send, sorry, let me back up a second, M distinct types of molecules. In this example, M will be 2. To send a 0, perhaps you send a molecule of type 1. And to send a 1, you send a molecule of type 2. Where I'm using different colors here to emphasize the fact that the molecules are distinct. So then at the receiver, obviously what you do is you try to detect which type. So this is this might even be a simple and obvious, maybe even the first type of communication scheme that you could potentially think of that implements molecular communication. But I do want to emphasize one point about it, which is that if you have 2 distinct and perfectly distinguishable types of molecules, you can use them instead as separate channels. For that reason, I don't tend to think very much about molecule shift keying. It's very simple, obviously. It's easy to think about. But really, if you had a certain type of molecule, you could then use that molecule with either timing or concentration. And if you had another type of molecule, you could use that type of molecule with timing and concentration. So in putting this in more conventional communication terms, it's as though you have 2 different frequency bands. So in other words, it seems kind of a waste to use them both at the same time to send 1 bit when you could use one of the other techniques to send 1 bit using type 1 and maybe the same technique to send an additional bit with type 2, and now you've doubled the information rate. It would be a bit like if you had 2 frequencies, F1 and F2, and you did some sort of frequency modulation where you sent a signal at frequency 1 for 0 and a signal at frequency 2 for a 1. Well, why not just use both frequencies at the same time to send independent streams of information? So this technique is used and it's widely described, molecule shift keying, but we're not going to say too much more about it because it's not the most intelligent use of resources. There's another basic one, which is quite new, and we're actually going to hopefully talk a little bit more about this in a later lecture, and that is space. So much like spatial space-time coding and related techniques in wireless communication, the location of a molecule's transmission and reception can be used to encode information. So this will lead to, there is a technique that, again, we will hopefully talk about, called molecular MIMO. And the concept works like this. If you have actually, let me not draw them as blocks, let me draw them as reservoirs. If you have reservoir 1 over here, reservoir 2 over here, and a detector there and a detector there. If you take a molecule from reservoir 1 and put it into the environment, chances are it'll probably get here faster than it'll get there. So when it arrives at the first receptor first, the first receptor gets a stronger signal from this than the other one. Then you'll probably see that the molecule is released from reservoir 1 as opposed to reservoir 2. On the other hand, a signal could potentially be released from reservoir 2 that would again be received more strongly at receiver 2 than receiver 1. So the choice, so much like spatial coding in conventional wireless systems, the location of the transmitted bit, or the transmitted molecule, excuse me, can be used to encode information. And in this example, you can easily see how it would work. If I want to send a 0, maybe I'll release the molecule from reservoir 1, and it'll probably be received here. If I want to send a 1, I will release it from this reservoir. It'll probably be received here. Of course, there's error because they could be received at cross receivers. And on the other hand, you could probably use, or you can definitely use, some sort of space-time code to ensure that the molecule is correctly received. Or in other words, you could perform more complicated signal processing to ensure that the symbol is more reliable. Again, we're going to hopefully talk more about that when we talk about molecular MIMO. But that is a technique. That is an important technique in molecular communication, and it's the subject of a lot of recent research. And finally, there is the hybrid techniques. So I alluded to this a second ago, but hybrid techniques, that basically means any combination of the preceding techniques. So for example, you could combine quantity and timing. Or you could combine quantity and space, as in MIMO. Or anything. These techniques that we've discussed, they are each degrees of freedom, and you can use them by themselves or in combination. Basically, each technique gives you a separate parameter to play with in order to design your message. So we are going to go into some detail on timing and quantity, and probably also on space to talk about MIMO. And that will be, that's how we're going to use the next few lectures.